Today we're going to be looking at proving the volume of a cylinder, cone, and sphere using integral calculus. So if we take a cylinder and we put it on the xy plane, it would be a rectangle, right? Because when you spin that rectangle around, you're going to get that cylinder in 3D. So if this slice right here in this rectangle, when we revolve it around, it's going to create a thin little disc. And when we add that disc to the next, to the next, to the next, an infinite amount of times within this 0 to h range, remember that volume turns into pi r squared dy with the disk method. Okay, so I have the whole video on disk method to see where that formula comes from. But in this case, we have a pi, and r for a cylinder, it has a constant radius, right? The radius is not changing. So we can pull that out of the integral as well. And where are we integrating from and to? Where are these slices moving from and to within this rectangle? Well, they start here at the bottom at 0, and they go through the entire thing, an infinite amount of slices, all the way up to h. So we're going from 0 to h, and left hand side is just a dy. Because the volume of one of these little discs is delta v, right? Which is base times height. Delta v is really just a little cylinder, right? So this is the base of a cylinder, a circle, times the height of a cylinder, which in this case is just a little change in y because of our coordinate system. Okay, so then we're going to take the limit as the number of these disks goes to infinity while summing them all up, and that's how we get the integral, right? So finally, the volume is pi r squared. The integral of dy is y. We're evaluating that at h and 0. So the volume is just pi r squared h. Right, so that is how you get the volume of a cylinder. So that one is not too bad. A cone is a bit more intuitive. When you wrap this triangle around the y-axis, it turns into a cone. This slice turns into a disk. So we're going to be using the disk method again. Volume equals pi r squared dy. Okay, but what is r? It's obviously no longer constant. This r is different than this r because we agree that this slice, when you bring it down to this cone, that slice becomes the radius of the cone. So let's look at this line, right? It's a line, so it has an equation mx plus b. We know what b is though. B is the y-intercept, and we know that is h, right? But what is m? M is a slope, right? It's rise over run. Let's see if we can figure out the rise over run from this picture. Well, between these 2 points, we can see that we're rising, or really going down, a negative h. So it's a negative rise, and then we're running a positive r, right? So the rise is negative h, the run is r, so m is negative h over r. So we could represent this line as y equals negative h over r, x plus h. Let's test this. What happens when x is equal to r? When x is equal to r, what is y equal to? Well, let me throw on the h as well. When x is equal to r, what is y equal to? Well, this r cancels this r, and you can see it's just negative h plus h, right? Negative h plus h is 0, so y is 0. Is that true? At an x value of r is y 0. Well, right here, you can see that y is 0 when x is r. So far, the equation works. How about if we make x equal to 0? What happens at x equals 0? Well, then we just have y equals h. Is that true? Right here, x is equal to 0 and y is equal to h. So yes, our equation works. This equation right here. We only have one issue, is that r should be a function of y because we're integrating with respect to y. But we have a function of x. So let's just solve it for x so that we have a function of y. This becomes x equals minus r over h times y minus h, right? So this is our radius function. So the volume we can find is pi, where the slice is going from and to again, Again, they're going from 0 to h. We said our radius function was minus r over h, y minus h squared dy. We can pull this r over h outside of the integral after we square it. So we have a pi r squared over h squared, right, because the negative disappears. Then we have the integral from 0 to h of y minus h squared. I'm going to choose to do a u sub for this rather than foiling it out, because if we just make u equal to y minus h, du is just dy, because h is just a constant, so we don't care about it. We only care about this y right here. So if we do that, we have u squared and du. But what's the issue? The bounds are no longer h and 0, right? Because those are y values. If we have a function of y, the bounds are a function of y. So that just means we have to plug in those bounds. What is u of h and what is u of 0? When we plug in h into u, we get 0. And when we plug in 0 into u, we get negative h. So instead of going from 0 to h, we're going from negative h to 0. This way, when we finish up the integral, we do not have to plug back in our function of y, because we already changed the bounds. So now we're going, when you integrate u squared with respect to u, you get 1/3 u cubed. We're evaluating that at 0 and negative h. So now we should get pi r squared over h squared times 0 minus, when you plug in that negative h, you're going to get a minus 1/3 h cubed, right? So finally, volume equals, we have that pi r squared over h squared times this negative and negative cancel, and we're left with just 1/3 h cubed. H squared on the bottom cancels the cube on top, and now you just have volume equals 1/3 h pi r squared. So moving on to a sphere, well, I'm going to do a hemisphere in this case, and then we can just double it to find the volume of a sphere. So with the hemisphere, once again, we can use the disk method, pi integral r squared dy. We got to figure out what r is, though. How can we represent this function? Well, it's part of a circle, right? So why don't we just call a circle x squared plus y squared equals r squared. We know we want to solve it for x so that we have a function of y. X is going to be equal to the plus or minus square root of r squared minus y squared, right? Are we going to choose the positive or negative, though? Well, we're already in the positive x in this case, so we're going to forget about the negative. This is x equals r, this is y equals r. Okay, so now this is our radius function, and we have that volume equals pi integral the radius function, r squared minus y squared, squared dy. Where are these slices going from and to? Well, they're starting here at 0, and they're going all the way up to r, right? Okay, so now we have v equals pi, 0 to r. The square and the square root cancel each other to be left with r squared minus y squared dy. Volume equals pi. When you integrate r squared, it's just a constant. So when you integrate it with respect to y, you get r squared y. You integrate y squared, you get 1/3 y cubed. We're going to evaluate that at r and 0. So volume equals pi r cubed minus 1/3 r cubed, right? Then pi r cubed minus 1/3 r cubed is 2/3 r cubed. So we have 2 pi over 3 r cubed. This is the volume of a hemisphere. So if you want to find the volume of an entire sphere, just multiply by 2 to get 4/3 pi r cubed. This is the volume of a sphere. Or we could have integrated these slices. Imagine we had an entire semicircle here. We could have started the slices at negative r and went all the way up to positive r. So if we had changed this bound right here to a negative r, it would have just had this same magnitude but negative. And when you subtract the negative, you add it. So it's really just like multiplying it by 2. Or you can find the volume of a hemisphere and double it. So that is how you find the volume of a sphere, cone, and cylinder using integral calculus.